of a raw dataset like an undisturbed crime scene. When you first step up to the door, your job isn't to start moving the furniture or running forensic tests. You stand at the threshold, observing the room to understand exactly what you're dealing with. Exploratory Data Analysis, or EDA, is a manual inspection phase. It is an iterative process of questioning your data before a single line of modeling code is written. To navigate this room, you follow a loop. First, you generate questions about your data. Then you search for answers by visualizing or transforming specific variables. Finally, you use what you learned to refine your initial questions and begin the cycle again. The objective of this cycle is to rigorously investigate the underlying quality of your records. This search phase is where you determine if the data actually meets your baseline expectations. Machine learning models blindly extract and memorize patterns. If you feed them unexamined, biased, or broken records, the resulting system will replicate those specific flaws with perfect precision. Translating that observation into code starts with a few commands to map the dataset's structure. Calling shape, info, and head allows you to quickly see the number of rows, the variable types, and a sample of the raw records. These commands yield concrete structural information. From here, you can identify duplicated entries or corrupted formatting and filter them out before they can skew the model's baseline understanding of the population. Manual data inspection lacks the prestige of building complex models, but it provides a high return on investment. It ensures you aren't building a sophisticated system on a flawed foundation. As you inspect your data, you must recognize datasets are rarely neutral. Bias exists in a continuous loop between user interaction, collected data, and the algorithm. Big data is inherently heterogeneous. Ignoring these distinct populations leads to aggregation bias. This chart shows the naive analytical view. Observing this population as a single mass suggests a strong, positive correlation. But when disaggregated into underlying subgroups, the trend reverses. This is Simpson's paradox. A seemingly positive correlation was actually 3 negative ones. Failing to identify these hidden subgroups results in models that deliver backward recommendations. You end up applying a generalized trend to populations that behave in the exact opposite way. Beyond hidden biases, you will inevitably find impossible measurements. Imagine scanning a database of users and finding a single age listed as 999 within a row of otherwise valid health metrics. The beginner's instinct is to discard the entire row to resolve the error and move forward. This approach rapidly shrinks your training set. If you discard an entire row for every single invalid variable across 50 columns, you risk ending up with a dataset too small to yield any meaningful insights. A safer alternative is to replace only the specific unusual value with a missing value indicator, like NA. Isolating these anomalies preserves the surrounding evidence. It keeps valid data in that row available for future analysis, rather than throwing it away. We have successfully mapped the dataset structure, disaggregated hidden subgroups to avoid bias, and isolated damaged values without deleting the records around them. This workflow reveals that most outliers and paradoxes have specific logical causes. What initially appears to be random noise is often just a pattern that hasn't been examined yet. However, we still have a problem. We've tagged our anomalies as NA values, but most machine learning models cannot process these gaps. To make our dataset whole, we have to move from observation to repair. In the next phase, we'll look at the mathematical techniques used to impute those Bayesian values.